Hello and welcome back. This is video 2 of lecture 1 in University of Physics 2. Now, in the previous lecture, we talked about simple harmonic motion, and I showed you through solving a differential equation that the solution for an object moving as per uniform circular motion is exactly the same as the solution for a spring or the solution for a pendulum. And that's because these are all examples of simple harmonic motion. What I'd like to do today is to begin talking about waves. So, waves are unusual in that they don't represent an object that has well-defined boundaries that moves from one point to another point in space. Waves are actually motion of a medium. So let's just go ahead and define that. Motion within a medium. Now, just to sort of give you an example as to what I'm talking about, what I'd like to do is to introduce you to sort of an idealized solid. Now, we know you have solids, liquids, and gases, and solids are defined in part by the fact that they hold their shape. So if you were to look at the inside of a solid and look at the arrangement of the atoms and molecules on the inside, you'd see them sort of sitting in what you could think of as almost a lattice. Now, there's this game that as a kid I used to play called Chinese checkers, which was a metal tin that had little dimples on the top. And what you would do is you would place marbles in the dimples, and that would be the board. So you can think of as these little points as those dimples, and in each dimple you have a marble, and that marble would be an atom or a molecule, whatever it is that makes up your solid. Now, it turns out that if you look at the forces that are holding this thing into its solid shape, the forces actually look a whole lot like springs. And in fact, we typically model them as such. So we model the interior as sort of a whole bunch of little points that are interconnected by springs, and the spring constant is, is related to the amount of force that would sit there between the atoms and molecules holding it into this shape. So what I'd like you to do is to think of sort of taking, we'll say, these atoms right here, and what we're going to do is we're going to pull them up like this. Now remember, these are all connected by what you can think of as springs. So what would happen when you pull it up like that is as this one goes up, because a spring is a floppy object and not a solid bar, there would be a slight time lag between this one right here and this one right here and this one right here, knowing about the fact that you pulled this up. So as you pull, we'll say just this one up, these guys follow. So this one goes up, there's a lag, the neighbor goes up, eventually following the path. His neighbor over here will say, there's a lag there. And if you were to shake this thing up and down, what you would have is you would have this up and down motion conveyed like this through the material. Now, what I'd like to be very clear about here is that you have something that appears to be moving to the right, and it is, we'll say, in this case. But the actual atoms and molecules that make this thing up aren't physically moving to the right. So it's this up and down shaking motion that's conveyed this way. Now, this is an example of a wave, and what you have is motion, and we know, as per our understanding of energy, that when things move, they have kinetic energy. So in this case, what you have is the ability to transfer energy from one point in space to another point in space without actually having to drag matter with it. So unlike a normal solid object, which is what we've dealt with, say, all the way through University of Physics 1, which has a well-defined boundaries. As it moves through space, it drags this matter with it. Waves don't do that. Waves are motion within a medium. And what they do is they allow us to transfer energy. They allow nature to transfer energy from one point in space to another point in space without dragging the matter with it. And as a consequence of that, the most common way that you see nature move energy around is through waves. The best example of which would be that of light. And we'll be talking about that later on when we get into thermodynamics. Now, that said, there are three basic types of waves, two of which we'll spend time talking about in this class. The third type I'm going to show you an example of, but the mathematics that describes it's pretty complicated. So in this particular situation right here, what we've done is we're moving the medium, the material up and down. So we're shaking it up and down like this. So this would be like the direction of our shake up and down. So this is the direction of the shake, like that. And then what happens is the wave that's created here moves side to side. So this one in this particular case, because we're shaking from this end, is moving to the right. You could shake it from this end, in which it would move to the left, or you could shake it from the center, in which the wave would move both ways. So you have that ability. We're going to be talking about that later on after we're done talking about the types of waves, because it's actually pretty important. So this type of wave right here, where you're shaking the material up and down, the motion is side to side, is called a transverse wave. Okay. Now, conversely, you could take your atoms or molecules here, and instead of shaking them up and down like this, you could shake them side to side like that. So as you pull them this way, what happens is your atoms and molecules, because again they're connected with forces that are a lot like springs, the sideways pull, we'll say like this, is slowly conveyed to its neighbors. So this one will move, and then there's this slow transfer of information where this one starts to move like that. So you can recognize this right here as sort of this shape right here, except now it's on the side. So basically what you're doing now is you're shaking the material this way. Okay. So this is the shake right here. And your wave also transfers this way as well. Now this type of wave right here is called a longitudinal wave. Okay. Now, a good example of a longitudinal wave would be a sound wave. And longitudinal waves are actually pretty important because it turns out transverse waves, when it comes to states of matter in which they'll move through, they only move through solids. Now, the reason why is because when you take these atoms or molecules here and you move them up and down, this up and down motion has to be conveyed to its neighbors via these bonds. But the issue that you have here is that in liquids, the connection between its neighbors are very weak. So you have weak connections to its neighbors. It's the reason why liquids can flow, we'll say, to fill a container. But if you were to look at, say, the top of a glass of water, and I encourage you to do this at home if you get a chance, you fill up a glass of water to its to very top, and then add just a little bit more, and what you'll see is that you can get a bubble over the top like this called a meniscus. Now, this meniscus is only possible because you still have these weak bonds between, the molecules of water inside that state. Now, the issue that you have is that those bonds aren't strong enough to convey this up and down motion to neighbors. So transverse waves aren't possible inside a liquid. And the same is true for gases. Now, liquids and gases both fall up under, the identifier of fluids because they flow. And gases here, the bonds from a zeroth order approximation are non-existent. A good example of which is for those of you that have had chemistry. The ideal gas law assumes that there are no interactions between the molecules or the atoms that are on the inside. And the first order approximation to that would be something like the van der Waal equation, which we'll be talking about when we get to thermodynamics, which is a very weak interaction. But in general, we assume that the atoms and molecules in there don't interact, except maybe through collision. And as a consequence, you don't have the ability to convey this up and down shake through a gas. On the other hand, longitudinal waves can pass through liquids and also through gases. And instead of them passing via these these connections between the atoms and molecules on the inside, generally the way that they pass through collisions. So, you may shake this guy back and forth, and as a consequence, he collides with neighbors. And what that does is to allow that shake to travel. That's the reason why sound waves can travel through air, and they can also travel, through solids and liquids as well. So, the two most popular waves, like I said, the two that we're going to be talking about in this class, are transverse waves and longitudinal waves. Now, on the other hand, there is a third type of wave, which is a little more complicated. And generally, what you do is you take a material and you twist it. So, for example, I could take, a good example, I guess, like a pool noodle or something like that, and twist it. So maybe I twist it like this and twist it back and forth. And what happens is that back and forth twist travels side to side like this. And so this right here would be an example of a torsional wave. And describing twists and things like that when you have a material, it's actually pretty complicated. So it's above the pay grade of this course, unfortunately. However, I will point out that in order to twist it, you would need to have these strong bonds in order to convey it. So once again, torsional waves only work in solids. So longitudinal waves, sound waves, work in all states of matter. But these other two do not. Now, so I'll be showing you some videos in this particular lecture here in a moment, so you can get a good idea as to, what these waves do basically as they travel. But before I do that, what I would like to do is to talk about some of the properties of waves that are not the same as the properties of a solid object with well-defined boundaries. So because waves represent motion inside a material, at least mechanical waves, which is what we're dealing with, and let me define that for you. So a mechanical wave travels via the bonds or the collisions in a medium. Now, by medium, I just mean material. Because of this, and because you're not dealing with an object that's traveling, you're dealing with basically motion. Waves can do a whole bunch of things that solid objects that have well-defined boundaries can't. A good example of which would be a trampoline. So if you've ever jumped on a trampoline before, and here's the surface of a trampoline, we'll say, and you've jumped on a trampoline with a partner, you know that you can give a bounce assist. So you can actually help somebody bounce if you look at the surface of just you jumping on the trampoline. It might bounce up and down sort of like this. Okay? And if you're able to take your up and down motion and time it just right with your partner's up and down motion so that you are going up at the same time that they are going up, if you do it just right, then what happens is your bounces can add to produce one enormous bounce like this. So really all you're doing is you're adding motion together. You're adding the motion of your bounce to the motion of their bounce to create one big up. And as a consequence, your friend goes flying way up in the air. On the other hand, imagine a situation to where you're bouncing on a trampoline like this, we'll say. And what you do is you time your up just right with their down. So when that happens, what happens is your motion of up and their motion of down add together to cancel each other out. So you actually still their bounce. And if you've jumped on a trampoline, you've probably done that before, at least with a friend. So you get no bounce at all. Now, this is entirely unlike any of the objects that we've dealt with before. For example, if you take a car and you collide it just right with another car, you don't suddenly get a bigger car. Nope, that doesn't happen. Just like if you take a car and you collide it with another car, you don't suddenly have your cars vanish. Okay? But because waves represent a phenomena that's just motion within the material, you can actually set up that motion to, we say, interfere, to either take two or more waves and interfere them together, okay, to create a bigger wave, or take two or more waves to interfere together to create a smaller wave. That's just a simple example. And like I said, this right here is called interference. Okay, when you add to create a bigger wave, we call this constructive interference. And when you add to create a smaller wave or no wave at all, we call this destructive interference. Now, in reality, it's more complicated than this because your wave may not play nice like these do. Okay, but that said, to get a sense of how these waves work, this is just introducing you to the terminology. Now, likewise, if you've ever sat outside of a classroom and you've waited for the person on the inside's lecture to stop, you know that you can hear the lecture. And yet the door is closed. How's this information coming out? Well, the person's talking will say in here, and here's this wave as it travels through the air. It's a sound wave. And what happens is it hits the wall. Now, when it hits this wall is made up of atoms and molecules. It's a medium. And what it does is it shakes the wall back and forth. Now, as a consequence, this side of the wall acts like a speaker. But some of the shaking travels through on the inside. It shakes this side over here and creates another wave right here. Now, when we talk, the information that we're trying to convey is trapped in what's called frequency and amplitude. And we're going to introduce those concepts here in a moment. Now, that said, what you see here is the ability for a wave to, we say, reflect, to transmit, and because there is some loss on the inside, which we'll be talking about more later on when we talk about thermodynamics, be absorbed. But if you look at the amount of energy that this wave contains, because remember it's moving, so it has kinetic energy. If you look at the amount of energy that's inside the wave, you add up the amount of the energy that's being reflected, the amount that's absorbed, and the amount that's transmitted, you end up with them equaling each other. Now, um, solid objects with well-defined boundaries don't do this. For example, if I were to ram a car into a wall, when it hits, I don't get a smaller car that bounces off, and I don't get another car that passes through somehow. And the car is not absorbed partially by the wall itself. So again, you have the ability of a wave to do something that solid objects don't. Okay? So they can transmit, they can reflect, and they can be absorbed. Okay? Now, so we talked about some of the properties of the waves, basically in general as to how, they are transferred through a material, the types of waves that you can have, some of the ways in which they differ from, an object and what have you. What I'd like to do now is to talk about just sort of some terminology that you see used dealing with waves. Now, what you're looking at here is, something you've probably seen in trig before. It almost looks like a sine wave or cosine wave or something like that. So what I'm going to do is I'm going to make this a sine wave by putting our y-axis here. So this is our y-axis. Here's our x-axis. Let me just highlight the axis right here. Okay. Now, so the waves that we're going to be dealing with in this class are going to be, very regular, very periodic waves. So, this part, for example, looks like this part right here, looks like this part right here, this part looks like this part, looks like this part, and so on, very regular waves. So that said, if you look at how high above the x-axis a wave can be, basically, and you compare that to how far below the x-axis this wave can be, you'll see that the heights or the depths are the same. Okay. Now, we call the height of a wave, in reference to it being flat right here, we call this right here the amplitude. It's abbreviated A. This right here would be the same. This would be an amplitude as well. Now, if you were to physically measure the distance between consecutive peaks, this physical distance right here, whether it's that distance right there or this distance right here, these distances are called wavelengths. Now, amplitude, we use A to denote it. Wavelength, we use the Greek letter lambda. All right. Now, so let's pretend that this wave here is moving to the right at a speed of v. All right. So if you were to stand here and look up at the peaks as they go by and measure the amount of time it takes for one peak to leave and the next peak to show up, you would have the period. It's the time between consecutive peaks. All right. Now, if you remember our conversation last lecture, if I were to measure the number of peaks that go by over time, we would call that the frequency, how often you see the peaks. But we also know that there's a relationship between the frequency and the period, and that's that frequency is 1 over the period. Now, so let's talk more about the speed of this wave. So the speed of a wave is determined by the properties of the material that it's traveling through. The reason for that is because it's riding along the bonds or it's traveling through collisions in that material. And that generally is something that's well defined by whatever the properties of the material are. So, for example, if I were to look at the speed of a sound wave in water, no matter what sample of water I'm looking at, as long as it's the same type of water, it's not salt or anything like that, the speeds are all going to be the same because the properties of all the water are going to be the same. And the same thing goes with air or with other things. As long as the properties are the same, the speed is going to be the same. So if I were to sit here and I were to watch this one peak leave and the next peak show up, the distance that that peak would have traveled would have been one wavelength. If I were to sit here and measure the amount of time it takes for one peak to leave and the next peak to show up, the time would be a period. Now we know speed is distance over time, lambda over t. But we also know that 1 over t, 1 over the period, is equal to frequency. So the speed of a wave is related to its properties in the following manner. The speed is the wavelength, the distance between two consecutive peaks, times the frequency, which is how often you see the peaks occur. Now, this is a true statement. This is, in general, true for all types of waves, be it mechanical or other, which we'll be talking about later on when we talk about light. Okay, so we have a relationship between the velocity of a wave, its wavelength, and its frequency. What I'd like to do now is to use a simple example of a wave to find a relationship between the speed of a wave and the properties of the material that it's traveling through. So to do that, I want you to think of a string that has a wave on it. This is sort of an exaggerated wave right here, just to give me something to work with. Let me move this over here just so it's not so causing my eyes to bug. Okay, so what we've done is we've sort of pulled the string up and plucked it and let it vibrate back and forth. You can think of this right here as though it's the y-axis and this is the x-axis. And this would be flat, no wave at all. So we pull it up and we release it, and it makes this descent this way. And it's going to vibrate back and forth, along this equilibrium position right here. Now, so what I'd like to do is to pick a part of this string, we'll say maybe this part right here, and zoom in really, really, really closely, sort of infinitesimally close, if you want to think of it like that, kind of like what you do in calculus when you're looking at how derivatives work. So we zoom in here and we get really, 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 really close, and what you'll see is there's a little bit of string there. We'll call it an infinitesimal element of string that maybe looks like this. All right, now to be clear, right here we're sort of working in, calculus limit land. So what I'm going to do is to mirror my x and my y coordinate system here, like this, centered on what we'll assume to be the center of this little bit of string right here. So here's y, here's x, and I want to remind you about how strings and how cables and things like that work. The tension at all points on the inside is the same, which means that if you think of this as being a little bit of mass, and I'm going to say it has a mass of dm. Now, why dm? Well, okay. The string that we're looking at right here is not an idealized string. It's not massless. It actually has mass, and typically what we say is it has linear mass density. So density is how much of something is in a volume, typically, right? So most people, your first experience with density would be through rho being mass over volume, or depending upon how it's defined, dmdv. Now, that said, there are area and there are line densities as well, which, if you remember from University of Physics 1, when we talked about centers of mass and stuff like that, we looked at a little bit of that. So right here, we have what's a line density. So the mass of this thing lies along the line of the string. And we're going to use the Greek letter mu right here for that. And it's basically the mass of the string divided by its length. Okay, so the units would be something like, kilograms per meter. So So if you think about this right here, sort of as you know, the template for how we're dealing with density, then our mass is going to lie along the string along dx and along dy, because remember, this is an infinitesimally small amount of string. Now, so here's the deal, though. I want to pick this thing such that the angle here, the amount of distance that's been plucked up, is very small. And the reason why I want to do that is because if you think about triangles and you think about, for example, the last lecture that we had, one of the things that I pointed out was that if your angle here, if your angle here is small, then if you think about sine of that angle, right? For example, the opposite side right here, the sine of the angle is going to be more or less just the angle. Okay, so if you think about cosine, sine, and tangent, and just to remind you, tangent is sine over cosine. Okay, it turns out that the cosine part, and you'll find this out in calculus too when you do series expansions. The cosine part, when you expand this as a series, it goes like 1 plus 1 over 2 theta squared, et cetera, and so on. So if your angle is very small, the theta squared part is gone, and cosine basically goes like 1 because your angle is very, very tiny. It's very close to 0. And if you think about how cosine behaves, cosine of 0 is 1. So what that means is that you can approximate cosine as a 1, sine as theta, and tangent as theta over 1 or just theta. Okay? Now, there's a reason why I'm pointing this out, and that's because if I take this element and I blow it up, so here I am going to expand it out. This is my little line element. It has a mass of dm. Again, the mass, even though it technically lies along dx and dy, dy is so small that it more or less lies along just dx. Okay, so the density here would be mu times dx. There's this much, this is the mass density, and this is how much of the string that we're looking at. We're looking at a little bit of dx part right here, okay? So, so anyway, again, I want to be clear about this. This little element of string has a mass of dm. Now let me get rid of that. And what I'm going to do is I'm going to redraw my coordinate system because I want to use this to argue out an equation that gives us a sense of what the velocity is going to look like based off of the properties of the string, its tension and its density. So let's see, I'm not very happy about that. Let me move this over here. There you go, that's better. Okay, so this, like I said, is an infinitesimally small piece of string. Okay, now the tension on this side is the same as the tension on this side, but this may not be a line. This might be an arc. And what that means is if I call this side 1, whoops, let me take this out of line mode. If I call this side 1 and this side 2, that our angles here might be different. Okay, even though the tensions and magnitude are the same. Okay, now here, remember, we're releasing this thing and it's going down. And also remember, the string itself is not moving to the right or to the left. We're looking at the wave on this thing. The string itself is just moving up and down. So if I were to sum up the forces here, okay, which you quote unquote have 1 if you want to think of it like that, that's going to equal to whatever the mass is of the string times the acceleration that it's going to experience. Okay, now I just want to look at the y part of our force. Okay, but I'm going to go ahead and show you what the x part looks like. So remember, this thing, this mass element, is only moving up and down. That's where it's experiencing acceleration. Side to side along x, it isn't. which means that if I sum up my forces along x, I'm going to get 0. And if you look here, we have a T2x, which is positive, and then we have a T1x, which is negative. And these, because it's not accelerating to the side along x, are going to add out to 0. Now, however, here along y, they are not. So you would have positive T2y, negative T2x. And what this is going to do is it's going to act on that mass to cause it to experience acceleration. And this acceleration is going to be along the y direction. Okay. Now, so that said, let's talk about what T2x and what T1x and what T2y and what T2y, it should be a y, look like. Actually, it should be T1. I don't know how that happened. I think I was just looking at the top. Sorry about that. There we go. T1y. That's better. Okay, so so here T2, T2x would be the adjacent part right here, which is going to be T times cosine of theta 2. T2y is going to be the opposite side, which is the sine part. So that's T times sine of theta 2. Okay, now T1x is going to look like T times cosine of theta 1. T1y is going to look like T times sine of theta 1. Okay, now check this out. Not only is this the way the tension looks, but if you think about, and let me use a different dashed line. If you think about how this thing is put together, that gives us a sense of how the angles work as well. Now, what do I mean? So watch. This right here on the right-hand side, I'm going to call dx, excuse me, 2. And this right here is dy2. This over here would be dx1, and this right here would be dy1. We're just looking at the right and the left-hand sides. Okay? So what that means is that if you think of looking along what's going on along the y direction here, okay? So remember, T2y, T sine of theta 2, T1y minus T sine of theta 1. This can be written as T theta 2 minus T theta 1. But look, theta, well, both sine and tangent act like that. So I could, knowing the fact that both of these act the same, with very, very small angles, I could write my thetas like tangents instead. Now, tangent is opposite over adjacent. And for theta 2, the opposite side would be dy2 over dx2. I'm going to call this dy dx in 2. Tangent of theta 1, which is the same thing as theta 1, would be dy1 over dx1. Or dy dx in region 1. Okay, so remember, this is the same thing as theta 2, and this is the same thing as theta 1, which means that the left-hand side of this equation right here, which I started off over here, I can write this way. T times dy dx in region 2 minus dy dx in region 1. Now on the right-hand side, I have dm times ay. So this right here would be the equation that describes how this thing is moving up and down. Okay. Now, so let's flesh this out a little bit more. And I will remind you that dm is equal to mu times dx. Also, ay is the acceleration in the y direction, or two derivatives of y with respect to t. Okay, so I'm going to take this, I'm going to write it over here, t times dy dx 2 minus dy dx 1 on the left-hand side is equal to mu times dx, two derivatives of y with respect to time. Now, I'm going to make a notation change here, and the notation's following. Y here, since this wave could be traveling back and forth, it's going to be changing with time. So the y position is going to change with time as this thing oscillates up and down over time. But we also know that as we go along the x direction, y is going to change as well. So y clearly is going to be a function of position and of time. But look, we're taking derivatives here in position and also in time. Now, there is a technique in calculus called partial differentiation, where when you take a derivative, you hold everything fixed except for the thing that you're taking the derivative of. So for example, let's pretend that your mathematical function looked like x times y. If I took the derivative of f, you see the cursive d here, with respect to x, I would hold the y fixed like it's a constant and just take the derivative of everything else with respect to x. So this would be equal to y. This says hold everything fixed except for the thing that I'm taking the derivative of. And since y is a function of both x and t, we need to express our differentials here in that manner. Now, I'm also going to take and move the t over here to the right-hand side and this dx over here to the left-hand side. You're going to see why here in a moment. But let me just go ahead and flesh this out. dy dx 2 minus dy dx in region 1 divided by dx is equal to mu over t, two derivatives of y with respect to time. Now let's look at this. If you remember the definition of the derivative, when you take the derivative of something, you take the limit as delta x approaches 0 of f of x plus delta x minus f of x divided by delta x. Now, here, looking at my picture, this right here is the same thing as this on the left-hand side. This right here is the same thing as this on the right-hand side. What I've done is to let the delta x go to 0, and in which it becomes a dx. Okay? So this is a derivative with respect to x, but there's already a derivative with respect to x. So on the left-hand side, what you have are two derivatives of y with respect to x. On the right-hand side, you have mu over t, two derivatives of y with respect to time. Now, this has a name. This is called the wave equation. It is one form of it. Now, that said, typically the way this is written is the following way. And give me a second. Let me sort of get technical about this. We move this constant stuff over to the other side. When you do, that flips those. So here's your generic wave equation. And what I want to do is to show, whoops, let me go forward with that. What I want to do is to show you really what this is right here. And to do that, what I want to do is to, if you remember when we looked at differential equations last time, what I did was to sort of use a solution for the motion of this thing on a circle, or of a thing exhibiting uniform circular motion. Just use the solution along x, and I showed you that satisfied also the spring and the pendulum. Well, you take the same sort of approach here, except now that our y is changing with respect to x and t, it complicates things a little bit. And the solution looks something like this. Okay, so typically it's y of x and t is equal to a times sine of. Now let me get my sheet here, because it's pretty ugly, because we're going to actually reduce this a little bit. It looks like 2 pi over lambda times x plus or minus vt. So this is sort of a generic solution to this. Now, what's the plus or minus mean? Well, the minus means that your wave is moving to the right. The plus means it's moving to the left. Okay. Now, we have this unruly 2 pi over lambda sitting out in front. And there's actually a way that we kind of clean this up a little bit. 2 pi over lambda is defined to be something called k. Now, this is not the spring constant. This is called the wave number. That doesn't make a whole lot of sense right now. It makes more sense whenever you take and you do. I don't want to do that. It makes more sense when you take and you do more complicated wave stuff, which if you pursue more advanced physics courses, you'll see later on. But I want to also show you that if you take 2 pi over lambda and you multiply it by v, you get something. And so remember, for a wave, v is equal to lambda times f, right? So if I take v and I divide it by lambda, that's the same thing as the frequency. There's a v over lambda right here, which means it's the same thing as 2 pi times the frequency. And you may recognize this as omega, the angular frequency. Okay? So when you take and you multiply 2 pi v over lambda, when you multiply all that stuff together, what you end up with really is omega. Okay? So what that means is that when you multiply this through, your solution ends up looking like a sine of k times x plus or minus omega times t. Okay, with this being k and this being omega. Now, so what's the point of showing you this? Well, what I want to do is I want to plug this general solution in here, carry out these derivatives, okay, and in my equation, and we'll plug that in. And then we're going to see how mu over t relates to things like k and omega. Okay, so let's see here. Let me snag this right here. I'm going to take this to another sheet. Actually, let me snag all of this right here. And I'll clean it up. Paste it here. And let me just sort of take the eraser after it because we don't need a lot of this stuff. I don't need this really. And then I'm going to take, whoops, move this there. I'm going to take and move this here. Move this here to remind us. And then this right here is what we want to work with. Okay. So here is my y as a function of x and t. All right. And so we're going to just take some derivatives of it. So I'm going to take a derivative of y with respect to time. That means we hold x fixed. It's considered to be a constant in here now. The derivative of sine is cosine. I'm going to choose the negative part because the negative part is the most common one that you see used because it represents traveling to the right. And we know in most problems, when we work them, we assume our object's initially traveling to the right, just to makes life easy. So if I take a derivative of this with respect to time, I get a minus omega out in front because this is a constant. An a, and it becomes a cosine. Okay, so if I take another derivative with respect to time, cosine becomes a minus sine. There's a minus omega here that comes out again, which hits this negative and makes it plus. Then you have the negative from here, which makes it negative again. And we get sine of kx minus omega t. Okay. Now let's do the position derivatives. dy with respect to x. If I look at this, there's a k sitting out in front. Derivative sign again is cosine. There's no negatives or anything like that. So this is just going to be a times k times cosine of kx minus omega t. And then I'm going to take another derivative with respect to x. Derivative cosine is minus sine. A k squared sine kx minus omega t, but with a minus sign out in front. And now I'm just going to plug this in right here to this, and this in right here to this, make some cancellations, and then see how all this stuff relates. So on the left-hand side, I have this minus omega squared a sine of kx minus omega t. On the right-hand side, I have a t over mu times a minus k squared a times sine of kx minus omega t. So a lot of cancellations, like I said. First off, the negatives go. Next up, the signs, those go. A goes right there, which means on the left-hand side, I have an omega squared. On the right-hand side, I have a k squared, and then there's this t over mu sitting here. Now look. If I look at this right here, and I look at this right here, and I say, okay, what do I get if I take and I divide omega by k? Omega is 2 pi v over lambda. K is 2 pi over lambda. Oh, wow, look at all that, a bunch of cancellations. I get v. This is the speed of the wave. So I'm going to move this k over here to the left-hand side. When I do, I have an omega over k squared on the left. On the right-hand side, I have a t over mu. But as we just saw, this is the speed of the wave. So v squared is equal to t over mu, or v is the square root of t over mu. Now, if I go back and I look at the wave equation and I note the fact that t over mu is the same thing as v squared, I can rewrite this. I can rewrite this equation. What I do is I get rid of this, and I put conventionally a c squared. The c conventionally is what means this is the speed of the wave. That's how you differentiate between the speed of a wave and the speed of a solid object with well-defined boundaries. We're going to use v because that's consistent with your book. This right here is the wave equation. Basically, if you can beat your physical situation into something that looks like this, if this is the equation that you get at the end of the day, you can immediately pick off what the velocity of your wave is going to be. And you know what the solutions are because it's already been solved. But this right here, though, is a critical relation. Okay. So this tells you the relationship between the velocity of a wave and the things that comprise what the wave is traveling on. The tension, which for a solid would be analogous to the bonds of the atoms and molecules that make that thing up, you know, how strong they are. And the density, which would be the mass density of the object. And in fact, typically, we say that in any given situation, really, the velocity of your wave is going to equal to what's called a restoring property over an inertial property. So, for example, in the case of a string, tension is the thing that's attempting to restore it. It's the force that's trying to, that's creating the tautness, if you will. And the inertial property is the mass. That's mass. Remember, is basically analogous to inertia. Okay. So let's take a look at some examples here. So what is the speed of a wave on the string? The hanging mass is 65 grams, and the string has a mass density of 1 kilogram for every 100 meters. If the string vibrator below vibrates with a frequency of 100 hertz, what is the wavelength of the wave? So let's draw a picture for this so you understand what's going on. We have a table. This is actually going to be a lab that we do. There are these little things that are called string vibrators that basically are boxes that have a motor in it, and that motor has this lip. It's like a tongue that has a hole through it, and you attach a string to it. Now, in the experiment, what you do is you take that string and you put it over a pulley, and what keeps the string taut is the fact that between the string vibrator not between, but on the other side of it, if you will, is a hanging mass. Okay? So it looks a little bit like this. So this thing right here is going to vibrate up and down with a frequency of 100 hertz. There is a mass hanging off the end here of 65 grams or 0.065 kilograms. And we're given the mass density of this string. It is 1 kilogram for every 100 meters. Okay. So we want to find the speed of the wave and also what the wavelength of the wave is when it's vibrated at this particular frequency. So let's write down our givens. We're given a frequency of 100 hertz. We're given that the hanging mass is 0.065 kilograms. We're given the string line density, which is 1/100 kilograms per meter. We're trying to find the speed of the wave and also the wavelength. Okay. Now, so if you think about this, we know that the speed of the wave is going to be equal to the square root of the tension of the string divided by the mass density. Now we have the mass density, but what we're missing is the tension. And the tension is going to come from the hanging mass right here. So if you think about force diagrams, if you were to draw a force diagram on this hanging mass and assume that for all intents and purposes that it is stationary, then you would have on the hanging mass its weight going down and the tension going up. And remember, the tension here is the same thing as the tension here in magnitude. So you have a tension up, you have the weight down, and again, we're going to assume that it's stationary. So when you sum up the forces, you get 0, which would be just the tension plus the weight. Now along X, nothing interesting, but along Y, we have the tension minus the weight equaling out to 0. So what that tells us is the tension is just equal to mg. Okay, so here for the speed of the wave, this is going to be the square root of mg over mu, or the square root of the mass, which is 0.065 kilograms, g, which is 9.8 meters per second squared, and mu, which is 1/100th of a kilogram for every meter. Now, if you do this calculation, and let me plug this in, it's the square root of 0.06 or 0.065 times 9.8 divided by 1/100th. Give me a second here. I get 7.98 meters per second. So if you take sig figs into account, and you assume 1 sig fig because of your 100 hertz here, and also because 1 kilogram for every 100 meters, then the speed of your wave here is going to be about 8 meters per second. Okay. Now, what about the next part, which is the wavelength? Well, to find that, we use the relationship between the speed of a wave, its wavelength, and its frequency. And we've been given the frequency. So lambda here is just v over f, really, which would be 7.98 meters per second divided by f, which would be 100 hertz. Now remember, hertz is 1 over second, so the 1 over seconds are going to cancel each other out. So if I were to divide this by 100, I'm going to get 0.0798 meters about. Or again, if you round it, 0.08 meters, or about 8 centimeters. So that's the wavelength. Okay. So again, a quick, easy example. Now, here's another one. You have a child's play guitar that has nylon strings that are 35 centimeters long. Now, the nylon itself has a mass density of 15 grams per meter. And what I want to know is what tension the string would need to be tightened to in order to make a musical note of E. Now, a musical note of E has a frequency of 329.628 hertz. What we're going to discover is that sound again is just a wave, and what we correspond or what we think of as a musical note or a pitch is actually just a frequency. Okay. So what you have here is a string basically that's suspended between 2 points, the neck of the guitar and the bass. So here's our string right here, like that. Now we know this distance. We know the distance between here and here It's 35 centimeters, and that's relevant to us because half of the waves, so half of a wavelength would be sitting here. Okay, so we'd be able to find out the wavelength from knowing this. So let's see here. So I'm going to call this D. It is 35 centimeters, or 0.35 meters. Okay. We know the line density of this is 15 grams per meter. So it's very light, or 0.015 kilograms per meter. Okay. We know the frequency of the note. It's 329.628 hertz. Now, what we're trying to find is the tension. Okay. So let's write down our givens. We know mu is equal to 0.015 kilograms per cubic meter, or per per meter rather. We know lambda is actually twice d. It's 2 times d. D is 35. 2 times that, it's going to be 70. But we need to note the fact that it has 2 significant digits. Okay. Now, so we know this. We also know the frequency of our musical note, which is 329.628 hertz. And what we're trying to find is T. Now, so previously we know we have this equation right here. Right? But we also know that V is equal to lambda times F. Now we've been given lambda and F. We know mu, and we're trying to find the tension. So really, this is a pretty easy problem. All you do is solve for T. So again, lambda is 0.70 meters. The frequency is 329.628 hertz. Now we are actually squaring this. And then we have mu, which is 0.015 kilograms per meter. Now, let me plug this into my calculator. Uh, 0.7 times 329.628. Going to square that. And then multiply that by 0.015. I get 798.6 newtons. Or if you round to sig figs, we have 2 here, we have 2 here, we have a whole bunch over here. Really, it's 2 at the end of the day. Is 800 newtons, or 8.0 times 10 to the second newtons to show the number of sig figs that we have here. So there's our tension right there. Now, so here, actually here, I had mentioned that the speed of a wave in a material is really just the restoring property over the inertial property. Now we can take this form of the equation and expand it to solids and liquids, and even gases under the right conditions. So if you think about it, we know that for a solid, if you remember our discussion back in University Physics 1, you have shear, you have compression, or tensile strength, and then you have torsion. These are the 3 ways that you can stress a material. Now, shear is analogous to a transverse wave. If you think about it, you're shaking the material up and down. Up and down is shearing action. If you think of your material lying on the side, that would be shearing, like using scissors. Compression is analogous to longitudinal behavior. And torsion, well, I mean, that's a torsional wave. Okay? So let's not forget longitudinal waves are sound waves. And that said, what I'd like to do as a first example is to look at water. Now, water has a density of, this is wrong actually, this should be 1,000 kilograms per cubic meter. And the bulk modulus, which is how well it resists compression or, restoration, is 2.1 times 10 to the ninth pascals. What I want to know is what the speed of sound is in it. Now, a sound wave is just a longitudinal wave. So if you find the speed of a longitudinal wave, well, you're set. And the bulk modulus is analogous to the Young's modulus in that it's a compressional modulus. Okay. So really, the speed of our wave in this case would be the square root of the bulk modulus over the density, the restoring force, the restoring property over the inertial property. Okay. Now, in this case, it's just the square root of 2.1 times 10 to the ninth pascals over 1,000 kilograms per cubic meter. Okay, so if you plug this into your calculator, let's see, times 10 to the ninth divided by 1,000, I get 1,449 meters per second, or keeping to sig figs, and this 1,000 is actually sort of an exact number. It's it ends up almost being like a definition. This ends up being about 1,400 meters per second. Now, this is water. All right. If you compare this to air, air actually has a sound speed, like at sea level at normal temperatures, of about 340 meters per second. So in water, air travels almost 4 times as fast. Or not air, but sound rather. Air travels 4 times as fast in water. That's hilarious. Anyway, so it's sound that does it. This is in part the reason why, if you're swimming underwater and you hear a sound, the sound sort of is garbled. And that's because your brain is designed to process sound that has a speed that's like this, and not sound that has a speed like this. Okay. There's also other reasons behind it as well, but we'll get to those later. So there's another example. What's the speed of sound? Well, it's the speed of a sound wave in iron, which has a density of 7,870 kilograms per cubic meter, and a Young's modulus of 210 gigapascals. And then I want to take a look at diamond. So for iron, we have a density of 7,870 kilograms per cubic meter, and a Young's modulus for iron of 210 gigapascals. That's times 10 to the ninth pascals. For diamond, we have a density of 3,530 kilograms per cubic meter. But we also have a Young's modulus that's incredibly high of 1,220 times 10 to the ninth pascals. Okay, so for this one, for iron, the speed, let's have it right there, sorry about that. The speed is going to be 210 times 10 to the ninth pascals divided by 7,870 kilograms per meter cubed. So if I plug this into my calculator, I get 210 times 10 to the ninth. Oops, that's a mistake. Oh, I did 2 square roots there. And then I'm going to divide that by 7870. I get a speed of sound of around 5,166 meters per second. 2 sig figs here, 3 sig figs here, so 2 at the end of the day. So about 5,200 meters per second. Diamond, on the other hand, which, is related to the densest materials that we have here on Earth, some of the hardest materials, actually, not densest. 1,220 times 10 to the ninth pascals divided by 3,530 kilograms per cubic meter. So if I do that, let's see. Is that divided by 3,530? 18,591 meters per second. Or if you look at sig figs here, about 18,600 meters per second. Okay, so the bonds in diamond, diamond is basically carbon bonded to carbon. These are the strongest normal bonds that we see in nature. What are they not? Covalent bonds, I believe, is what they are. So these are the strongest bonds that you see in nature. These right here. That's the reason why diamond is so hard. And you look at iron, though. I mean, this is 5.2 kilometers per second. This is 18.6 kilometers per second. Okay. So anyway, now you see some of the properties of waves. You see how the speed of a wave relates to the properties of the material that's traveling through. Now, I'll be back in our next video on this lecture, and we're going to finish up our discussion about waves so that we can move on and start talking about thermodynamics. And I will see you then.